Okay, today we're going to be talking about a couple of battery basics, specifically 12 volt automotive style system battery basics. And there is an enormous amount of information to talk about. However, we're going to cover some of the most typical things you'll come across, or uh, most typical questions people have initially when they usually are starting from zero knowledge. So that's going to be the focus, and there'll be multiple videos covering the facets of batteries. So we're looking at a rough drawing of a typical 12 volt system battery that's similar to what you'd find in an automotive system, like a car as an example. And what you're going to want to determine is what is good and what is bad. So a lot of people think it's as simple as 12 volt battery. If it measures 12 volts, then I'm good. And there's more to it than that. So now we go from a side view to the top view of the battery. And what we have is the individual cells. Now, the specific battery you have, they might be maintenance free. You're not going to have an obvious view of the individual cells, but on the older style and a lot of batteries, they still have these 6 individual caps that you can see here. These individual cell caps, and a lot of them had a slot for a slotted screwdriver to undo them and perform maintenance on them. But most of the newer styles do not have that, regardless of the exact composition, whether they're AGM batteries and so on and so forth, absorbed glass mat. And this is just some generalizations to get some people started, and then they need to learn the specifics about their specific battery. So the older style of the lead acid, they had these 6 individual cells that you can see here, and each one of them has a rating approximately of 2.1 volts DC, volts direct current. So each individual cell, as you can see here, 2.1 volts, and then I have an ellipsis, so on and so forth. So 2.1, 2.1, and 2.1, and if you add that up, you end up with 12.6 volts. So when I was saying earlier that it's not as simple as a 12 volt battery is 12 volts and I'm good, if you measure that, really what you want to measure is 12.6 volts to know that you have a fully charged battery. So the point is the useful range, because there's a lot of ranges that the batteries can be, but what we're concerned about is a useful range, a range that'll actually do something. As an example, start the engine in your car. So what that range is 11.9 approximately to 12.7 approximately. And for purposes of this video, don't worry about a fully charged battery is 12.6 and 12.7. There's a lot of approximations, and it varies for a lot of reasons that there's no reason to even get into that detail for everyday usage. Just keep in mind that, you know, approximately 11.9 to approximately 12.6, 12.7 is a fully charged battery. So if you only measure 12 volts DC, volts direct current, you have an almost dead battery. You are not good. And depending on the situation, especially concerning electronic control modules, even if you have enough voltage and amperage to crank over the engine, the electronic control module may not let the engine start because it has a minimum voltage that it wants to see before it'll turn the other systems on, allowing the engine to start. So keep that in mind. So for measuring, we use a multimeter. This is a crude drawing of an analog style meter as opposed to a digital style. But it gives you the basic idea. You have your positive and negative, and if you're going to measure the open current voltage, you simply connect the positive meter lead to the positive battery post and the negative meter lead to the negative battery post, and you measure what's called the open circuit voltage. And that's simply, you're measuring an open circuit as opposed to a closed circuit. So a closed circuit is a complete circuit. Positive to a load, in this case we have a motor, and to the common or ground, and in this case the negative terminal of the battery, and then of course there's flow within the battery. So we have a complete circuit, or otherwise known as a closed circuit. So when we're talking about open circuit voltage, we are talking about measuring only the battery. It's a open circuit. We don't want the whole circuit, as in the case with the closed circuit. We just are concerned about the battery voltage, and we don't want the rest of the system involved skewing our results, because we're focused right now on just testing the battery. So I have a couple of terms defined up here. So 12 volts direct current, OCV, if you see that somewhere, someone talk about what they're talking about, is 12 volts direct current, open circuit voltage, meaning measure just the battery. That's what they're talking about. So 12 VDC, volts direct current, so that's what that equals. And I mentioned here we have a multimeter. What is a multimeter? A multimeter is a voltmeter plus an ohm meter plus an ammeter. So a meter, you could buy these separately that just measure volts, just measure resistance, measured in ohms is the unit of measurement for that. And you could buy separately a ammeter that just measures amps, just measures current. But commonly we use multimeters because it's multi-function. It measures many things all in one meter. So that's what we're talking about there. So now we are ready to measure our open circuit voltage, once again, meaning now we're ready to test the battery by itself. And we don't want it hooked up to the system, skewing our results. So what we need to do is, one, we need to take a measurement before charging so we know where we are at, because it might be important in our troubleshooting, meaning it might be, if the symptom is my car won't start, you know, it is one piece of the puzzle that's going to tell the story of what's going on here. So measure your open circuit voltage before charging, then you're going to charge the battery fully, meaning 12.6 volts approximately, and then you are going to test it. But before you could test it, you have to remove what's called the surface charge. And the surface charge, I have a layman's definition up here. Surface voltage or surface charge is the wimpy voltage left over from the system running or charging. So if you're measuring your open circuit voltage with the surface charge on there, it's going to once again skew the results in another way. It's not going to give you a good, useful reading, because we're not worried about anything except what's actually usable for us, what's usable for starting the engine, what's usable for running any sort of load. And that's where we come into removing the surface voltage. So we don't need to get into the science for right now of what system voltage is, or how it's there, or why it's not as useful as other voltages. All we need to know right now is we want to remove it so we get a real reading of our open circuit voltage of our battery. So we will remove it by turning on, in the example of the automotive system, all we got to do is turn on our a pretty high load for a duration. And in this case, easy one is turn on your high beam headlights. And most of the time 30 seconds will do it. Some manuals will tell you to do it for a couple minutes and so on. So the circuit and the load capabilities and everything, as far as how long high loads can be for what durations, the situation will dictate. But keep it simple, just turn on your high beams for 30 seconds, and that should, in most cases, remove the surface charge. So then you get an actual reading of your open circuit voltage. And you want it to be, 12.6, 12.5, something like that. You don't necessarily freak out, if it's not that, because once again, so, this is labeled useful 12 volt OCV open circuit voltage range, but really we know that essentially the useful range is basically 12 to 12.6 or 12.7. So keep that in mind. Another common thing is this phenomenon of setting a battery on concrete and that concrete will kill it. In reality, it has nothing to do with concrete, save for the fact that concrete is a great heat conductor. So it conducts heat away from whatever is touching it very well, similar to metal. Metal is a great heat conductor. So that's why you wouldn't want to set it on concrete, but once again, the fact that it's concrete has nothing to do with it. You don't want to set a battery on any surface that will conduct heat away from the battery rapidly, making a differential, making a difference. So in this example, we have a battery sitting on concrete, and the concrete is less warm than the air, because we could say the air is warm and the concrete is cold, but it's more correct to say we have something that's a certain temperature and then something that is less warm than that, and all it takes is less for there to be, once again, a differential, a difference in the temperature. So in this example, we're going to use 90 degree Fahrenheit and 60 degree Fahrenheit. We're going to assume that the concrete is 60 degrees Fahrenheit and the air, meaning the ambient air, meaning the surrounding environment air, is, so if it's a garage as an example, if the air is 90 degrees, then the ambient air is 90 degrees. So, and then the concrete is 60. So it's not like there's such a huge difference. It's not like negative 460, and it's 100 degrees Fahrenheit in the air. This is the more realistic differential in temperature. So this is, it doesn't even need to be this substantial. There doesn't need to be this number of degree difference to cause a drain in battery. So long story short, if you set a battery on concrete or metal or basically a tile floor, any floor that's going to be substantially less warm than the air, it's going to drain the battery without anything hooked up to the battery because of this differential. And how that works is, you can see I have these simulation of lead plates, as a rough image of part of the internal structure of the battery. So we have these vertical plates, which are lead, and in this case, the bottom of the plates is going to be cooler in blue here than the top of the plates in red, effectively making them, so to speak, a dissimilar metal. When you have, that's how the battery works, is between the positive and negative, you have dissimilar metal, and then you have electrolyte flowing through the battery. So between the dissimilar metal and the medium, which will conduct electricity, that's how you get flow, and that's how you get potential or voltage, and that's how the battery works essentially. So you do not want dissimilar metal going on as a concept inside your battery besides that which is designed in the battery. So here, just pretend this is a piece of metal. It's a bar of steel, any type of metal, and on one end we have it in something, it's touching something that is 60 degrees Fahrenheit, and on the other end it's touching something that is 10 degrees Fahrenheit. So I've drawn this delineation here just to give you the idea that one end of the metal is a different temperature than the other end of the metal, and in effect, as far as what's useful for what we're going to experience, is that now you can actually consider this a dissimilar metal, even though it's not actually a dissimilar metal. Okay? And that's why that is important. So what you want to do is, if you're going to set it on a surface like concrete or metal or tile or even linoleum, it doesn't matter. If it's going to set it on a floor that's substantially cooler than the air, you want to have some sort of insulation. It could be anything that insulates, and it is a buffer of the temperature differential here. So it could be a stack of wood, like 12 inches of wood, or stack a few 2x4s together or something. Use anything. Use any sort of insulation. That way it's not in contact with that surface that will conduct the heat away rapidly. Another common thing is dirt on top of the battery. Okay, and this is a very interesting drawing of these little squiggly lines here. Just pretend that's dirt and acid on top of the battery. Okay, and that is a big deal, because you can actually take a multimeter, put the negative lead, the common lead, to the negative post, put the positive lead to this dirt and this almost always acid. There's a small amount of acid that leaks out of the battery and sits on top of the battery, and you will see voltage. And you seeing voltage means that the battery is being drained without a load from the car, and it is from this load that is drawing voltage out of the battery from the dirt and acid on top of the battery. So keep the battery top clean. You want plastic, clean, shiny plastic. And a side note is on your posts, you can get all sorts of acid and different things that you've probably seen on there. Keep them to not just metal, shiny metal. That oxidation is a little bit of resistance, and it all adds up to the end result of something not working the way you want it to. Another common thing is when, just try to visualize your bolt and then your nut going through your clamp on your battery post, and it can be all the way tight as shown here, and then there's still a gap in between the battery post and the internal part of the clamp. So you want to make sure that it's the properly sized clamp and that the bolt doesn't run out of threads before it actually gets tight. So you need to physically grab the connector and move it to where, make sure it's actually tight on the post. It's not enough that the nut is tight and you think it's tight. You need to physically check it, and then you want to make sure that there's no gap in between the clamp and the post. Whether it be a gap with acid and things built up, and dirt and otherwise oxidation, it will keep electricity from flowing from the clamp to the battery post. So you don't want air or anything else as far as a gap in between those. Another common thing is if you're going to load test it, as opposed to measuring your open circuit voltage, you're going to use a load tester now, and there's lots of different types. There's algorithm testers and carbon pile, and you need to orient yourself, just know when you'd use which type of tester. But for purposes, we're just going to talk about a general concept here. So you have your negative lead of your load tester hooked up to your negative lead of your battery, and your positive to your positive on your battery. Well, it's very important because most of the load testers use jaws, something like this. Rough drawing here. So the teeth on both of the clamps, you can picture you have a small surface area, just testing electricity from the small surface areas of where each one of those individual teeth contact the post. Individual teeth. I wrote here, small surface area equals pore contact, and pore contact equals pore flow, and that's what you're measuring. You're measuring a flow of electricity here. So you're already disadvantaged using a style that has clamps, but that's, you know, what's readily available, and it's not that big deal. You could do some good testing with these clamps, but you just need to pay attention to how you're connecting them to the battery. So in this case, these lines are indicating threads, and and this will be a studded type of post, as opposed to a post type battery that even this top piece would be lead. But in this case, we have a probably a zinc coated threaded stud with these. If you look on a battery, there's at the base there's these lead pieces, and you can see here I tried to draw picturing the clamp around this lead and in contact with this lead, not the studded post, because what you'd be doing, you know, I wrote here, picture the quality of a connection between the tooth of the thread and the tooth of the tester on the clamp. So you basically have a small surface area just on the tip of the tooth, and then you're connecting it, and it's only contacting on a tip of a thread. You know, you're compounding how bad your test is going to end up being. So you want to increase as much surface area as possible, so connect it to the lead at the base in the example of threaded post batteries.